In the third video of radicals, I'll be simplifying radicals. When we say simplifying radicals, really, we want so for example, if you look at example 1a, what we want to do is we want to reduce the radicand as much as possible. So I'll be doing two tacks or two methods here, and as you can see, I've done some preliminary work. So what's really important is in one method, you're going to have a good command of perfect squares, perfect cubes, and perfect powers of 4. So in my columns, I have perfect squares, and right here, perfect squares. In perfect cubes, there they are, and perfect powers of 4, there we are. So those are the numeric perfect squares, perfect cubes, and perfect powers of 4. And algebraically, for variables, I've also tried to list these. Now, you should have these on the top of your head. If you don't, we're going to have to use another method. And so, for example, this is the prime factorization. So I'll try to do some examples with each. So I'm going to just start off with the square root of 50, and I want to simplify this. The question that I'm going to ask myself, very similar to last year, is what is the largest perfect square that is a factor of 50? And those are the numbers that I'm thinking of right here. So do you see any of those that are a factor of 50? And anyways, it's 25. So I'm just going to simply decompose 50 into 25 times 2. And then I'm going to use the product rule for radicals to be able to split up my radicand into 2. And this turns into, I can take the square root of 25, and that's 5, and what's left over is the square root of 2. Now notice I split this up into a perfect square, which is in green, and a non-perfect square. You may ask yourself, why did I split it up into a perfect square and a non-perfect square? And that just is simply because I can take the square root of a perfect square. Another method to do it is 50. So I'll do this in red, and this is the prime factorization method. So I'm just going to do the square root of 50. And here I'm going to write my index 2, and this really doesn't matter. So I do the prime factorization of 50 aside, and I recognize that 50 is 5 times 5 times 2. So instead of writing the square root of 50, what I'm going to do is, since my index is 2, I'm going to be looking of groups of 2. So there it is. I have two factors of 5. So I would write it's 5 squared times 2. And very simply, I can decompose this again by calling this the square root of 5 squared times the square root of 2. Now, the square root of 5 squared can be simplified just simply 5, and that is the square root of 2 can't be simplified, root 2. All right, 90. So I'm just going to simplify this square root of 90, and what I'm going to ask myself is, do I recognize that if there's a perfect square that is a factor of 90? Absolutely, and that is 9. And so I'm just going to write 90 as 9 times 10. I'm going to decompose that as the square root of 9 times the square root of 10. Now the square root of 9 is 3 root 10. And that's the final answer. Now, how do you know when to stop simplifying? And really, it gets down to, does there exist a perfect square that's a factor of 10? No. 10 only has a factor of 2 and 5. So there's a lot of sort of mental math that needs to go on with this method, but it's fairly quick. Now, the prime factorization method might look a little bit different. So this is the square root of 90. Now, I'm going to split up the square root of 90 into its prime factors. So, and what we see is I've already done this over here beforehand. So I'm going to group, since it's a square root, I'm going to group 2 factors of 3, and then times 2 times 5. So I can split this up into 3 squared times the square root of 2 times 5. I may want to multiply those out to be 10. And I know that I cannot simplify, or my radicand is as simple as it can be. Now, on the expression the square root of 3 squared, I can simply write 3 root 10, exactly what we've seen. Hope this helps out. Now, perhaps one more example that I'll continue on. 2, why not? So it's the third root, or the cube root of negative 54. Now, the convention is that when we try to simplify the radicand, we try to make the radicand as positive. So I'm just going to try to think, does there exist a perfect cube that is a factor of negative 54? Sure, and that is negative 27. So somewhere over here, oh, yeah, right there. We're talking about perfect cubes, so I have those written down. It's really easy to write them down quickly, and it makes your mental math work a lot less. So plus and minus 27 are perfect cubes. So what I'm going to do is I'm going to write 54 as negative 27 times 2. I'm taking the cube root here. Now, I split it up into 27 because 27 is a perfect cube root. So now I'm just going to take the cube root of negative 27 times the cube root of 2. The cube root of negative 27 is negative 3 cube root of 2. So cube root, what we could do is, if you look at the prime factorization, we can just simply split this up into prime factorization. What you notice is that it's a cube root, so you're going to group them into groups of 3. I'm going to, since it's negative 54, I'm going to say negative 3 cubed. And by the way, I better put my index on that root, times my leftover factor of 2. So I'm going to split up my radical. So it's the cube root of negative 3 cubed times the cube root of 2. And what we have here is negative 3, the cube root of 2. Numbers are easy. They're nice. So let's go on to something with variables. The fourth root of 9 to the power of 4. What I'm going to do is I'm going to ask myself, does there exist a factor that is perfect power of 4 of 9x to the power of 9? And what I can do is I can split that up into x to the power of 8 times x. And this is the fourth root. And this sort of brings in the notion that the exponent that you're trying to, of your radicand, needs to be a multiple of your index. So 8 is a multiple of 4, and only then are you able to split it up. Or sorry, only then you're able to simplify this. So I'll try to show you a different way. Here we are, so I'm going to split this up. So there we have it, times the fourth root of x. So the fourth root of x to the power of 8 is just simply x squared. And the fourth root of x is the fourth root of x. If you're wondering why the fourth root of x to the power of 8, well, it becomes apparent if you choose, that radical, why is that simplify into x squared? It becomes apparent if you write it in its rational exponent form. So what we have is we could write that as x to the power of 8 over 4, where the index is 4, so that's the denominator. And since 8 is the exponent, that is the numerator. So that simplifies x squared. All right. If I'm doing the prime factorization method, it might look like this. I'm going to look for groups of, here we are, I'll just write it below. So this is x to the power of 9 as the fourth root. So since my index is 4, I'm looking for groups of 4 factors. So there's one group of 4, and there's 2 groups of 4. And I have x left over. So what I could do is I could decompose x to the power of 9 as into x to the power of 4 times x to the power of 4 times x to the power of 1. And you can decompose this into x to the power of 4, the fourth root of it, x to the power of 4, the fourth root of it, times x to the power of 1 and the fourth root of that. So x to the power, or the fourth root of x to the power of 4 is simply x. X to the power of 4, the fourth root, is simply x. The fourth root of x is simply the fourth root of x, and you can't simplify this. And really what we have is x times x, which is really x squared, times the fourth root of x.